Uh, so today's topic is going to be maybe a bit deep for any of who of you haven't really done much coding or much testing or studying computer science that much. But anyway, I try to keep the presentation at some kind of a bearable level so that everyone will enjoy at least some of the poor jokes I've hidden inside the presentation. There will be some really hard to understand theory about computer science and language theory, but also there's going to be some poorly written Python code, so you get something to laugh at. So there's going to be some demos and lots of talk about languages. But a few words about myself. I really liked the previous presentation done by Ilya about his background. So my background is actually in theoretical physics. I started studying theoretical physics in the late 90s, then decided that this is a really old science. All the easy problems have already been at least defined, if not solved. So it felt a bit intimidating. So I was looking at my friend who was studying computer science at the same time, and all he did was code Pascal. So, okay, come on. so I decided to change my major to computer science. Fast forward a few years, I started studying Masters of Business Administration, and in the meanwhile, I have been participating in founding lots of security-related companies. A few of them are listed here. I'm currently working at Silverskin, as I have been for the past 12 years or so. I'm working as the Chief Development Officer, which means I mostly design stickers. So lots of the stickers are in the box, but I have plenty more, so if you happen to run out of the cool, foxy stickers, you can always come to me and ask for more. Anyway, but currently I'm studying at the University of Jyväskylä, so I'm doing my PhD work there. Woo! Yay! Fellow students from you. So basically, what I'm doing there is conducting, let's say, fundamental research about software vulnerabilities and looking at them through these like formal language lenses, because there are lots of truths that have been mathematical, logically proven in the 60s, 50s, and so on, but none of those theories have so far been applied to software security. There are some groups that have done like the pioneering work, but there's lots of like stuff to be done. So comparing cybersecurity or software security to theoretical physics, well, this is the easiest way to go, basically. But one of the nice things of having been participating in several companies is that, as you can see, these are roughly the areas we work in. So if you think about the life cycle of a cyber attack, you first start doing some kind of threat intelligence, you use that information to build or plan an attack, then you conduct the attack, and of course you need to have some kind of incident response in order to improve your security processes. So it has been really nice to be working in three companies to see like the same domain, but from very different angles. Anyway, so let's get to it. Yeah, and because the event is sponsored by SANS, this is a shout out to SANS, so thanks for being there. When we first started our journey into cybersecurity, we extensively went to the US to study cybersecurity. So I myself have been completing a few of the certificates back in the day. This is a picture from our office, and this is something we did a few weeks back. There's one of my colleagues who succeeded in completing this kind of a security challenge that happened at the SANS conference. Because this is about languages, I decided to give the agenda or the structure of the presentation as a finite state automaton. And as some of you know, you can always equate these kind of state machines with a regular expression. So there's a regular expression that could match my presentation. Anyway, so this is also one of my favorite pastimes, thinking about sentences that can be interpreted in several ways. So syntactic ambiguity. And this is a really nice definition from the Wikipedia about a garden path sentence. So it's a sentence that has been structured in a way that when you're reading it, you automatically try to misinterpret it. And here's a good example. Well, there should be an example. This is one of my all-time favorites. Like, I don't understand how a snake even begins to organize a trip like that. So this is the kind of phenomena we're studying, but in the computer science domain. So how could we trick a program into parsing a sentence or input or whatever in a way that is syntactically correct, but it's the wrong interpretation? And this is the topic for today. So one could imagine that if you had an XML like this, so it is so simple grammar that there's absolutely no way of making a mistake of like creating this kind of a derivation tree by parsing. Yes, there's like some nesting elements, so you can have like it can be a very, very deep structure, but basically the structure is very simple. But already, this is like 2 years ago, so in iOS, there was this horrendous bug due to XML parsers. So inside iOS, you had 3 different XML parsers that did the parsing in a bit different way. So one of the parsers did parse the XML comments in a different way than the other ones. And there happened to be this very happy accident in the way these parsers were like executed in the validation chain, so that if you inserted these malformed XML comments, then the next parser would like inadvertently think that they were okay, and that was the reason this kind of bug was able to operate. So it's really not that let's say theoretical topic. These things happen all the time, and with like companies with great reputation even. So of course, like we want to know if this is if this is a kind of a bug that we could trigger automatically or find these kind of problems. And of course, like the name for this kind of phenomena is parser differentials. So basically, you have the same grammar for the XMLs, but the parser implementations differ somewhat. And this is like a very critical example of what could happen then. And of course, like you use parsers all the time in the compilations, so it's not only in the iOS domain where you use this. Anyway, so let's start from the very beginning. So this is a beginner's course in formal language theory. So the topic is using context-free grammars for fuzzing complex input languages. But we first need to understand what is context-free grammar. Well, the grammar is basically something that is used to define the structure of the syntax. And if we think about something very common, something we all know, like adding and subtracting numbers, multiplication, we can define the grammar for the arithmetic operations like this. So we have something called non-terminals, and we have something that is terminal. And an example is the best. So let's say we have this kind of very simple task to do. So this is an input for the program, and we need to parse it. So we need to understand what does what. So we always start from the beginning, so from E, and this, of course, can be any of these. So the first, in this case, the E becomes E of E, and then we always go for the left-hand side. So because E can become num, we did that, and the num can become any of these. So now we have 1, and we're left with the OP. So it can be either one of those. So it's that one, and then we're left with the E. And once again, this clicker isn't really doing it. Basically, that's the way we can do this. It looks like I need to be closer to the clicker. So finally, we have arrived at some kind of a syntactic presentation of something that we, like in our ordinary lives, would understand immediately. But we need to tell the computer these extra steps in order to define it. And we can create this kind of a, oh, what's happening here? Okay, yeah. There's imaginary lines. So this should be a tree structure. It doesn't, for some reason, show up. But basically, as you can understand, for arithmetic operations, we can have like an infinite tree structure. So it can be of any kind of complexity. And this kind of tree model we now need to keep in mind for the rest of the presentation. So these kind of derivation trees we are using in order to create these fuzzing inputs. All right, so let's continue. So fuzzing is a concept that we commonly think is creating random input, and that is correct. But let's say we try to fuzz a calculator. So if we create this kind of input, the calculator won't be able to do anything with it, because it doesn't really follow the syntax that we just showed you. Of course, if we just use numbers and plus and minus and so on, we can still end up with some kind of bits that really don't belong to the grammar, and this still won't work. So we need a way to somehow use the grammar in order to generate input that is syntactically correct, so that the calculator would read it in, and then we can try to see what kind of harm we can do. Maybe we can set the calculator on stun, we don't know. That could happen. So yeah, we need to use this kind of a definition in order to generate something more harmful. And let's now switch to something more interesting, if we can. Maybe not. All right. So I'm going to show you a couple of demonstrations from this really nice resource called the Fuzzing book. The Fuzzing book is a website that contains a lot of the code I'm going to show you guys today. So if you get any ideas of building your own grammars or building your own fuzzers, look no further. This guy who has written this Fuzzing book has like generously given out all the code for free. So I'm mostly using what he has done. So let's start off with doing some basic running. So in the first case, we can generate this kind of random fuzzer. And of course, it just produces random output. And of course, you can use this for good or fighting crime. But if we want to do these arithmetic operations, we can create this grammar definition in Python code. We can build even a syntax diagram out of it. Let's see if it works. So yeah. So this is how it works. So first we have the expression. It can become either term plus expression and so on. So it's recursively defined. Anyway. And now we can fuzz that grammar. And in this case, you can see how the derivation tree actually is being processed. And now we got this really nice input out of it with lots of pluses and minus signs. All right. So if we... OK, now we happen to generate this very complex-looking thing. And here is the resulting parse tree for that expression. So it's really extensive and really large. So basically how this using grammars for fuzzing works is that because there's an infinite amount of possible trees, you use the randomness of the fuzzing to create a random tree structure, and then you can basically use that approach to generate syntactically correct stuff, but it is still random, because you cannot enumerate every single arithmetic operation. there's this guy who is a math teacher coming up next, so he can even give you guys a proof of how you cannot do that. Anyway. Also, we have this really cool thing about like a mutation fuzzer, which creates this kind of small mutations into the input. So you can also give this mutation fuzzer some other fuzzer as an input, so it creates these seeds, and these seeds are then mutated just slightly. So let's give it a go. And well, sometimes you get something really weird looking like one at sign there. So it mostly looks correct. It might be an arithmetic operation, but we don't know if let's say these parentheses are balanced or that kind of stuff. All right. So let's move to something more useful. So as a pen tester, and especially when we are dealing with, let's say, web stuff, many times the parameters sent to, let's say, an API or some form. Those parameters can be defined using these grammars. So let's think about like URLs or emails or whatnot. If you want to generate some kind of URLs randomly, it just won't work. But luckily we can use this kind of URL grammar, and then we can use this kind of grammar to generate something that is more up to the challenge. So this is the grammar for the URLs. So you have your scheme, you have these specific bits, and lots of optional stuff. And now we can use this to generate weird-looking stuff. And of course, you can take these as a random seed for the mutation fuzzer to arrive something more interesting. Let's see where we went. It's really hard to scroll because I can't see the code on my machine. Okay, so this is what I tried to run. Okay, for some reason it... Oh, okay, yeah. So the point I was trying to make is that you can create these grammars by just typing in the structure, but you can also, as a tester, you don't always need to be that pedantic. You can skip a few places if you like. So in this case, here's the labels list. So if you think about these URLs, you can also use file contents to maybe I can show it to you. Okay, it's pretty small print, but basically you can take these commonly seen words like used for directory names or file names or path names. You can insert them directly so you don't end up having like completely random stuff. So you can somehow direct what kind of fuzzing it produces. Okay, let's see. So here we go. So as you can see, here we have gotten some of these path items from the labels text file. So let's say if you are doing some content discovery, when you're doing a pen testing against a web app, you see like what kind of directory names there are, what kind of naming schemes has to be used. You can use that to your benefit and try to generate something that resembles what you have already seen, but it is always syntactically correct, so it makes everything much faster. And of course, you can also put these guys into work, so you can generate something that is almost a URL, but not quite. And you can use these kind of inputs to maybe bypass some filters or to just test out if your URL parsing is working properly. All right. So one of my favorites is using JSON, because that is something that we are using almost everywhere. And of course, you can use a JSON parsing to also generate some nasty stuff. Okay. So now why would we do this? Of course, is the, the question in everyone's mind. Well, if you have built your own JSON parser, you want to try out if it works properly. So if it really can parse what the syntax or grammar definition tells it to be, but also the next level in the processing, meaning the application code, might expect the content to be something different, and so you can come up with these weird test cases. And of course, like, not everything created by these kind of fuzzing techniques is okay. Like in this case, I produce something that is syntactically correct, but there's still a parse error because there's a string got undefined. So there might be some semantic properties that are not automatically correct. So in order to do that, then you needed to add more code. But the basic starting point of using context-free grammars is that you don't care about the semantics. You only generate something that is structurally okay, and then it's for the next phases in the parsing and semantic analysis to see if it works correctly. All right. So let's go here. So these kind of inputs have been proven to, well, maybe proven is a too strong word here, but basically these kind of techniques were used by the author, and they were able to find 2,600 different parser errors, especially JSON parsing errors. And they were able to cash out like 50,000 euros from bug bounty programs, because so there are so many JSON parsers out there in GitHub. You can Google it, and not all of them have been like created the proper way. So this is a technique that really can put those parsers into a lot of trouble. But it's not always about creating this kind of harmful or maybe weird stuff. You can also use these kind of parsers, I mean grammars, to generate stuff that allows you to find more stuff. So the last example about I have here is let's say if you're doing some kind of hostname enumeration, let's say you are trying to figure out the attack surface of an organization, you only know basically the main domain names that they have, and you want to maybe do some kind of guesswork. You want to try out what are all the subdomains they have and that kind of stuff. So you can have a hostname grammar that defines what the format of these domain names have. And let's try this one also. And then, based on what you have found from the real world, you can use this kind of a probabilistic grammar fuzzing technique. So based on, let's say in this case, let me show you. So I took something from the DNS dumpster. So these are the Apple's Apple subdomains, and what we are interested is understanding like how deep these subdomains go, and also what kind of structure they use in their naming scheme. So how many times they have, let's say, dash there? Do they have like number prefixes or postfixes? We want to understand like what is the format or the structure of the naming scheme, and that we can learn because we can give our probabilistic grammar these samples, and then it will dig out the probabilities. So in this case, Let me run this one first. In this case, we are analyzing all the Apple's subdomain names, and it will give now some kind of an indication, like how many times there was a subdomain with only characters, how many times there was a characters, dash, and more characters, and then we can do this kind of recursive definition, so label can become label and characters and so on. So in this case, it only counts the occurrences, so how many times we saw this kind of structure. Also, this gives an indication how many times we found the subdomain name from our own ready-made text file, and how many times there was a miss. And now it gives a probability that in 0.06 times the subdomain was using this kind of structure. So this gives you far more control over when you're doing this kind of guesswork, because you see what kind of naming schemes are not used at all. So none of the times there was a random characters and then this name from the file. It was always something else, and this has like every fifth of the subdomains was using this structure. So you can understand the naming scheme based on this sample approach. And also, because by default all these derivation trees are generated randomly, you can also add, sorry about the scrolling, yeah, here we are. So if you're using this probabilistic grammar fuzzing, you can always add probabilities yourself. So if you are interested in finding something that has a test or prod or admin somewhere in the subdomain, but you are not picky about where, so it could be test dash something else, or test one dash something, or test dot something. So you can increase the probability of using any of these. So it will generate like these candidates with these probabilities. These probabilities, of course, can be very handy. Let's say if you're analyzing a web app that eats JSON as input, so you can gather from all the log files what kind of JSON structures you have found, and you can invert the probabilities, so you can generate those kind of inputs you didn't see. And because you're using the grammar, then it's always syntactically correct. So chances are that you're going to find some weird corner case. So this is really advanced stuff. And also, there's one more layer to the where you can control this generation of fuzzing input. So in this case, I have something called a loaded hostname grammar. So in this case, when in the derivation tree we go into one branch, which is in this case is labels dash characters, we can tell that the labels part, because it's none here, so it means the labels come from the file randomly, but the characters are not generated randomly. It is a random integer from that range. So you can have this kind of like a pre-processing or post-processing to all of this otherwise randomly generated stuff. And you can like optimize the way you are mining for the new host names. And this is very, very handy when you are doing this kind of attack surface stuff. Okay, so let's try to run this one. So in this case, I put so that in the case that we go to this branch, the random number is from 1 to 10, then the next one is 11 to 20, and you should be able to see from these resulting words that there's a logs 15, which means that, okay, we have then found the logs from our files, and the characters in this case is randomly from that range. But as you can see, there can be some very, very complex looking stuff. So there you have randomly generated most of the stuff, but you're still picking towards like ink and tag and whatnot from the file. So you get lots of control over to what kind of stuff you're generating, so it doesn't necessarily need to be this kind of very complex stuff and random stuff, but you get to decide like where the randomness is located in the structure. All right. Yeah, there's some feedback in the sound, but anyway, as the last thing, I'm going to show you one JSON parser 0-day I found a few years back. Those people who have maybe joined like software developer training sessions I have kept a few years back may recognize this one, but I think for the most people this is new stuff. So basically, what we were assessing or doing penetration testing against was this kind of a web application, and we only had access to the login page, and we didn't have credentials. And it's this kind of an example, so it's posting something to the login endpoint, and there's some JSON going as a parameter. And of course, in this case, you typically start up with trying to add some like weird characters into the password field. You try to fuzz it, you try to, let's say, arrive at the SQL injection, something like that. But in this case, nothing worked. It was bulletproof, it looked like. So all these fields were validated correctly. So I was not able to do any kind of a basic overstop 10 kind of attack there. But then it occurred to me, like, what about the JSON parser itself? Maybe there's something wrong with that one. And then I tried what happens if I just send the empty brackets. So I don't use this like what it's been expecting, but just something empty. And then, of course, things started rolling out really nicely. So, of course, there's no usable value for username because there's no username. But luckily, I also got a stack trace. And in the stack trace, you are always looking for something open source. And in this case, we found this LiftWeb JSON library. And I Googled and found the source code, and then started looking for problems with the parsing. And there are a few interesting stuff, like what happens if the parsing fails. There's a parse exception that is outputting something that's in the buffer. Okay, that could be a way to do some cross-site scripting, maybe. There's some stuff I didn't understand back then. But of course, the interesting stuff is like how the parsing itself works. And in this case, it matches characters one by one until it finds something that is not on the list, and in that case, it fails. And when it fails, it says unknown token and outputs what the unknown token was, and then we get the rest of the stuff. So I looked all these cases through and found there's no match for new line character. So let's see what happens. So what happens if I enter that kind of stuff into the parser? So as expected, we got unknown token exception. Very good. But these lines were like a bit hard to interpret, but there's some kind of offset happening, and there's something happening near what the buffer contains. So I was thinking, maybe if I had more characters, maybe there's more stuff in the buffer, so maybe I get a better exception next time. So I added some underscores, and then the killing character. So now I got a different kind of error. And in this case, I get the number 48, but there aren't 48 characters. So this is something else. But because this looked like a good strategy to just add the underscores, well, now it starts to look very interesting. So what the hell is happening here? Anyway, because this strategy seems to work, so let's just keep on adding more underscores. And now we need to understand or remember that I'm not logged in yet. Thank you. So I'm not logged in yet. I'm trying to log in. So whose information I'm seeing right here? Because I can see a phone number, I can see session ID, what else? Salt, I don't know what that's being used for. But anyway, so something is definitely bleeding out. So I had to take a closer look to the memory management portion of the JSON parser. This is Scala code, and as you maybe all know, Scala is famous for having a really bad memory management because it's using JVM. So for some reason, the developer had decided to create their own memory management. So you have the segment size, and if you run out of the segments, then you give back this possible element if the pool exhausted. So you have some kind of memory pool where you pull out segments and you give it to the parser. But if the parser fails, then it outputs what was previously left in the segment. So that was other people's correctly passed data. So I could leave this on a loop for a couple of minutes, and then I could able to harvest out all the other people's session tokens, and of course you just create a cookie and in you go. So a few pointers. So writing your own JSON parser is not easy task, and also writing your own memory management is not an easy task. And if you happen to combine those both aspects into one file, well then you have what's basically a Heartbleed JSON parser edition. Right. So that was fun. So now if we think about the web app domain for a few more minutes, there's lots of parsing happening at all times. So if you have an engine Apache in the front, the HTTP is the language it needs to understand. The next guy in the chain maybe parses JSON, maybe XML, maybe there's just some post data, like raw data from the HTTP, depends. And the next layer then processes whatever has been deserialized, and maybe it generates other languages based on what it has been reading in previously. So there are lots of different languages flying around, and the question is who should do what kind of validation? Because if you generate based on that, if you're trusting this parsing to be correct, then you generate a SQL statement, and then you have a SQL injection maybe. And also there's the question about what if we have a web application firewall? Doesn't that take these nasty problems away? If that were the case, then the WAF needs to understand all these languages, and it needs to be able to parse all these languages. And will it be able to do that? I doubt it. So this is really complex because it's a string of different kind of grammars, and nobody's really taking the responsibility of validating everything. So that is one of the challenges in the web application security, that you have lots of different kind of parsers, lots of different kind of languages, and well, you basically don't know if they are doing the job correctly. Also, this is really hard stuff, but basically, when we're doing input validation using regular expressions, then we are limited to this kind of a domain in the overall scheme of what kind of languages there even are. So, as you saw, the grammar definition for JSON was really complex. So there's no regex that can ever match that. So you need to use something more expressive. And then you get to this really high level of stuff, but we're not going to touch that. But just to understand that you need to match the validation routine with the input language complexity. So if you are only dealing with raw data with like key value pairs, then the regex might be good enough, but it depends on what the value is. So if the value itself is a complex input language, then you of course cannot rely on that doing the matching properly. And also what is not a context-free grammar, what can't you do with context-free grammars is of course something context-sensitive. So if you have a protocol message that relies on some field, let's say in this case you have the header or some length, so when you're parsing that, you need to read the length first and then you need to match something else. With JSON and that kind of like context-free grammars, you don't need to read any length, the structure is all you need to understand. All right. Final piece of advice. Maybe 10 years ago when we were doing these SaaS courses, in the material there was this kind of a really nice founding principle that prevention is ideal, but detection is a must or it is mandatory. And of course, back then we thought this is all about threats. So there will be some security threats that you cannot prevent, you can only detect if something is happening. For example, you cannot prevent phishing from happening. You cannot prevent the bad guy from sending a phishing message, but you can detect that and then you can respond to it. It's easy to understand. But this also applies to software development and also to software testing. It would be really nice to prevent a mistake from happening, but that only would be ideal. So we cannot really prevent someone writing a buggy code, but you need to be able to detect if that happens. So that is why you always need to test, because otherwise you are relying that, well, we didn't make any mistakes, and of course that's not happening. So, please do this. All right. That's all I had to say about this.
Thank you, Jani, for an excellent presentation. Please raise your hand if you have any questions for Jani. I have the mic, so I will bring the mic to you. Any questions? Yeah?
Hi.
Hello.
Can you hear me?
Yeah.
Okay, so
So the question was, can I hear him?
yes, good.
Yes.
Can you embed, let's say, well, best description is packet in packet. So, for example, take the whole syntax of everything and then put it to a string, but escaped. Do you get?
No, I didn't.
Okay, so meaning that if you have the whole like parsing tree,
yes.
Can you embed that inside of a string and have that escape so you would find attacks like packet in packet?
I think that is close to deserialization. So basically when you are packing the tree, then you are serializing what's in it.
Yeah, more or less, yes.
But maybe we can have a chat later for more in-depth answers.
Does anyone else have questions?
Here?
Yep.
Can you hear me now? Yeah. So, which version was the proof of concept that you showed fixed in?
Sorry, can you repeat that?
The 0 day you showed. Which version was it fixed in?
I have no idea.
Is it fixed?
Well, I did disclose it at the time, but I haven't since checked.
Good to know. Thank you.
Hey, thanks for the interesting presentation. Considering the grammars, Do you think that writing it using that grammar syntax instead of just writing straight out code that randomize one of HTTP, HTTPS, FTP, randomize one from this file, do you think one is easier, or do you think it's completely irrelevant to this approach if you straight out write code or use the grammar syntax that you demonstrated?
There was quite a many questions, but writing those grammars to begin with is pretty hard. But for some of the famous or known protocols, you can just Google for them. But of course, there are cases where that might be too much. It depends. But maybe we can also have a chat later. I will think about a better answer.
Okay. Any questions? Any more questions?